Okay, hello all and welcome to this quick short video. First off, I want to note that I'm just recording this on my laptop at school, so the setup's not quite as good as what I have at home, so the audio might be a bit hit and miss and so might the visuals, but making do so I can get this done nice and quickly. So this video is looking at an alternative method to solve solve circular function equations. Okay, so we're solving circular function equations, and we're going to do what I'm going to call, for lack of a better name, true substitution. Okay, so this comes from, we're going to use this when we have a situation like this where we have some operations inside the trig function. So this is something we can use when we have operations inside the trig function, just to make our life easier. It makes the process more straightforward algebraically. It's requiring a little bit less logic skills. There's still some interpretation. Okay, you're still going to have to remember your exact values for certain angles or use the hand trick, but this should work fairly well. It reduces the amount of logic steps and more just basic algebraic process. So the first thing we're going to do, whatever's inside our trig function, we're going to simplify it. Okay, we can use any symbol you want. I would suggest avoid using theta and avoid using x and avoid using t. We want to use something that we're not going to come across in problems very often, so that we avoid confusing ourselves with what variable is that we want and what variable we're using to do the substitution. So I would suggest using alpha. So I'm going to let 2 theta equal to alpha. Okay. And from there, if theta needs to be in the range in the domain 0 to 2 pi, it follows on that alpha must be an element of, and this is sort of like the previous method where we had a working domain, applied domain, and all those sort of things, or true domain and working domain. This is just making it more concrete and rigorous, I guess you could say. So if theta is equal to 0, that means alpha in that case would be 2 times 0 using our substitution rule. We're just using this. Okay. And then the 2 pi would turn into 2 times 2 pi. Again, we're just substituting our endpoints, okay, into our substitution equation. So it follows on that alpha needs to be the element between 0 and 4 pi. Okay. Also, if 2 theta is equal to alpha, we can say it follows on that 6 cos alpha, okay, minus 3 root 3 is equal to 0. Okay, that's why we've picked whatever's inside. Okay, that's why we've picked that to simplify this down. So we just get cos of something. And it makes our life a little bit easier. And so we're just going to use normal algebra to solve or to simplify this. So we're going to have 6 cos alpha is equal to 3 root 3. And we have cos alpha is equal to 3 root 3 on 6. So we get cos of alpha is equal to root 3 on 2. Okay, where, and we can take this down here, okay, we have our corrected domain, okay, or our working domain. We could use the same title as the previous method, where alpha needs to be the elements between 0 and 4 pi. Okay, so we now just need to solve, okay, cos of alpha is equal to root 3 on 2, where alpha is between 0 and 4 pi. So what are angles that make that work? Well, the most obvious one, okay, the one that comes to mind is our one in the first quadrant. So alpha is equal to pi on 6, is that right? 30 degrees is root 3 on 2, yeah, okay, is pi on 6, okay. we need to keep going because we need to do any angles up to 4 pi. So just quickly, we can have a think of, okay, so our first one is pi on 6. Now, because it's positive, the only other time that cos is positive is in the 4th quadrant. So pi on 6. Ooh, what have I just done? I've pressed something on the bottom. Okay, that's a bit of a pain. I'm at the very bottom of the page. Let me do that a little bit higher. Okay, so we have pi on 6 there, but we also have the equivalent one, which is pi on 6 down, which is actually the same as going around 2 pi, take away pi on 6. So we have 2 pi, take away pi on 6, which is fine. Okay, that's our 2 in 1 full revolution, but again, we have to go to 4 pi, which is 2 full revolutions. So what are angles that make that work? Well, we could go all the way around and then go another pi on 6. So we've got 2 pi plus pi on 6. Okay, that works. And the other one we could go is go all the way around 2 pi, and then we go around again until we get to this one down here. Okay. So that would actually be the same as 4 pi minus pi on 6. Okay. And you could get those all from symmetry identities as well. So we found our alphas, which I will rewrite over here with some space. So alpha is equal to pi on 6, and I'll simplify our fraction. So 2 pi minus pi on 6, that's going to be 11, oh my god, 11 pi on 6. 2 pi plus pi on 6, that's going to be 13 pi on 6, and we have 23 pi on 6. Okay. So that's pretty straightforward. Okay, we just did a substitution, we got a whole bunch of angles, and the only probably tricky bit for most of you should hopefully be this bit, which is just using the symmetry. Okay, we need to keep remembering that it's not just one angle that's ever true for a certain cos value. There'll always be 2 within a unit circle, and then if we're allowed to do multiple revolutions, well, we get more and more and more solutions. So that is getting our alpha, but what did we actually need to solve for? We need to solve for theta. Okay, we need to solve for theta. We've got some alphas, okay? So we need to go back to our original rule, or our original substitution that we had, which was 2 theta is equal to alpha. Okay, so therefore theta is equal to alpha on 2. So we can now substitute back. Okay, so this is really similar. Okay, if you're starting to notice, as we simplified something inside a bracket, this is where when we had those complex quadratics. It's very similar to that. Do a substitution just to make our life easier, solve the problem, and then resubstitute or undo the substitution at the very end. Okay, so if theta is equal to alpha on 2, it follows on that theta is equal to pi on 6 divided by 2, 11 pi on 6 divided by 2, 13 pi on 6 divided by 2, and 23 pi divided by 6 on 2. So we get our final solutions that make this work is pi on 12, 11 pi on 12, 13 pi on 12, and 23 pi on 12. And that's it. And we could now look back to our original requirement. Theta needs to be between 0 and 2 pi. Well, that's right, that's right, that's right, and that's right. All of them are between 0 and 2 pi. And we are done. So nice and short description. We'll call it true substitution for lack of a better term. Yeah, if you have any questions, ask in class, shoot me an email, put something on Compass. Completely happy to help.